network construction, as Mike already said. And as we probably all agree, the ultimate goal of many phylogenetic studies is to construct a species tree, like I have tried to indicate with my little cartoon here. Now, due to the computational complexities involved, which Tandy was going in her talk yesterday, what we can do, we can't get the species tree directly, so what people usually do is they try and derive the species tree from gene trees, which are indicated on my bottom line here. Now, if the gene trees are all in the same taxa set, then we can use consensus method to obtain our species tree. If, however, the gene trees are in different taxa sets, as indicated here, then things start to get a bit more complicated. And things get even worse if we have conflicting evolutionary scenarios, like here, where my gene for my tree and my human go together against the gene for my frog and my lion, whereas here I have my tree and my frog versus human and lion. So what can we do? Well, one possibility is to say, well, I don't like this. I just get rid of my tree here. That's one possibility. Another possibility is to say, well, I don't like the fact that I have my trees on different taxa sets, so I simply ignore the taxa which are in one tree and not in the other, which means in my case here I would simply ignore the gene one for my bird. But this is clearly not very satisfactory. Well, at least I think so, but that might be so what can we do? Well, if we want to include these conflicting information, then we have to go for a supernetwork approach. And the only supernetwork approaches I know of are C-closure, which was introduced by Hewson, DeSulian, Klöpper, and Steele. And then there's also Q-imputation, which is introduced by Holland et al. But both these approaches, although very attractive, have one major problem. If the input trees are very contradicting, then you tend to produce many, many splits, which has people led to thinking about filtering methods. One of them is the homoplasy filter, which was introduced by Hewson, Whitfield, and Steele. But the question is, can't we do a little bit better? Can't we be more careful when we are generating these splits or when we are putting these trees together? And as I already mentioned in some sense, the key is to say, well, from a combinatorial point of view, trees can be thought of as split systems. Thus, ways to generate or put trees together is to think of them in terms of trees, and then for the missing, to think of trees in terms of split systems, and then for each split where we have missing taxa, decide on which part of the split the missing taxa is going. So using this idea of thinking of trees in terms of split systems, one way of trying to generate fewer splits is to think of them, or to think of the concept of weak compatibility. Now, weak compatibility was originally introduced by Bundle and Dress in '92 in the context of split decomposition. Now, to remind you what weak compatibility is, I suggest we look at this funny-looking picture here. So we have three splits. The first one is this one here, which is left against right, A1, A1 bar. Then the second one is my split here, which is A2 against A2 bar. And the third one is indicated by my circle here, which is my A3 against my A3 bar. That's three splits. And assume I can arrange them in this funny way here. Then what I can do is I have intersections, triple-wise intersections. And if we look at these four triple-wise intersections which I've indicated by my black dot here, then weak compatibility says for any three splits, one of these four intersections here must be empty. If this is the case, then the split system is weakly compatible. So for example, if we look at for the case of for my argument, if we assume that this intersection here, which is A1 intersected A2 bar intersected A3, is empty, then what we can do is we can arrange the 4 intersections here, this one, this one, this one, and this one, in the form of this Y here, where the central part is taken by my empty intersection here. But clearly, this intersection, these triple Y's intersections, they don't depend on the fact that I've used splits, which are just partitions, or bipartitions. So I can also make or think of this kind of arrangement of my 4 triple Y's intersections in terms of partial splits, which are just splits on subsets of some tensor set. Now, what you see here to the left is my arrangement of my 4 triple Y's intersections, as you have seen before. But now my splits are A1, A1 tilde, where A tilde is just denoting the complement of my A1 here in some subset of X. Because S1, which is A1, A1 tilde, is a partial split of X, which means a split of some subset of X. Now, what our Y-inference rule does is, if for any 3 splits, I can find parts, which I might have to relabel, so I have this triple Y's arrangement, triple Y's intersection arrangement, then I can make myself 3 new splits, which is just my old split S1, where I keep my part A1 and I extend or add the intersection of A2 tilde intersected A3 tilde to my A1 tilde. So I just canonically extend in a systematic way. Now, the Y-inference rule, as we will see in a minute, has some interesting properties. Now, one property in the context of phylogeny is that it should be such that if I have 2 trees which come from a supertree, then the method should actually reconstruct splits that are displayed by my supertree. Now, the Y rule can't do this. It relies on the fact that I always have 2 incompatible splits, which means splits which can't be represented by the same tree, and I then go from there. So the Y rule on its own won't do. Now, I have to go away from my PowerPoint presentation for a moment, because when I looked at my presentation this morning, I realized that the next rule I want to talk about is not the right one. The reason is there are 2 rules that got originally introduced by Meacham, and by Murphy's law, I put the wrong one on. So I have to move over here. So I already said Meacham's rule. Now, Meacham in 1997 introduced 2 inference rules. One of them is the C-closure rule, which underlies the C-closure supernetwork approach, which I mentioned before. And the other one is the rule you see here. And it's a pairwise rule. And so you have 2 splits, S1, which is A1, A1 tilde, and S2, which is A2, A2 tilde. And now you say, well, if the intersection of A1 and A2 is non-empty, and the intersection of the complements, respective complements, is non-empty, then you associate, or you build yourself the split, which takes A1, A2, A1 intersected A2 against A1 tilde union A2 tilde, and you do the other one too, namely you take A1 tilde intersected A2 tilde against A1 union A2. Now, this Meacham rule has the nice property that if my 2 original partial splits can get displayed by a tree, then these 2 generated splits can also be displayed by that same tree. Okay, so now we have 2 closure rules, namely my Y rule and my M rule. So what kind of properties do they have? Are they just interesting, funny-looking rules, or do they do anything sensible? Well, we claim they do. Namely, that's the wrong inference rule, you can do the following process. Well, as I said before, the Y rule takes partial splits, generates partial splits, and so does the M rule. So what you can do is this. You take a collection of partial splits which are displayed by your input trees. You apply the inference rules I was talking about before, and you add the generated splits to your original collection of partial splits. Now, if your underlying condition, namely what's formed by the y, is violated, you stop. You don't do anything. And then you remove partial splits that can get extended by other splits in this collection, where the extension is the concept of extending is defined here, and you go back. So you keep applying this process until the process stabilizes, which means you don't generate anything new. Okay. Now, clearly, the question now arises, well, if I keep doing this and doing this and doing this, is it order dependent? How much does it depend whether I've applied to my splits, partial splits, S1, S2, S3, and applied my Y rule? Or what would have happened if in the first step, I had applied my Y rule to S3, S4, S5? So how order dependent is this? And it turns out that actually, if I have a split system which is irreducible, I mean, a collection of partial splits, meaning no split in my original collection of partial split extends another split in that collection, then, and my inference rule is either the Y rule, the M rule, or Y rule and M rule, so I just choose one or the other while I'm doing this process, then any two closures of my collection of partial splits obtained via my inference rules are the same. Now, it is important to notice that if I, at any stage of my process, encounter a situation where my underlying condition is violated, for example, in the context of my Y rule, I can't, in all of my 4 triple-wise intersections of interest are non-empty, then I'm dead. Then my closure would be just the symbol omega. If I never have the situation that all of my 4 triple-wise intersections of interest are non-empty, then I can keep going and going and going, and then I have a closure, which is the set described here. So now we know that we are order independent, which is quite nice. But what else? Are there any other nice properties in this context? And the answer is yes. And to explain what property we have, or have been able to show, I have to remind you of the definition of a circular collection of splits, which will then lead naturally to the definition of a circular collection of partial splits. So what's a circular collection of splits? Well, you have 3 splits here, and these 3 splits are circular because you can arrange the elements 1 to 7 around a circle, as I've done here, so that intersecting the circle with straight line cuts the circle into two pieces. One piece giving the vertex set of one piece is one part of the split, the vertex set of the other part is the other part of my split. Now, using this definition, or this idea for a circular collection of splits, we can say a collection of partial splits is said to be displayed by a cycle. In other words, it's circular if every split in my collection can get extended to a full split, such that the resulting split system is circular. It's very natural. So why is this of interest? Well, it's of interest to us because we have the following very nice theorem. Namely, if we have a collection of an irreducible collection of partial splits, just remember, we don't have no split extends any other one in my collection of partial splits, then my original collection is displayed by a cycle if and only if the closure of my collection via the M or Y rule, or the M or Y rule is displayed by C. Meaning, if my original collection of partial splits can be represented by a cycle, then what I'm generating with either applying my M rule or my Y rule will get, or is also displayed by the same cycle, which is quite nice. And in addition, we have the same result if the closure is only obtained by using the Y rule or just the M rule. Okay, fine. So from a combinatorial point of view, these two theorems are quite nice. But what does it have to do with phylogeny? Or why, is there any nice application? And the answer is, as I think, yes. And it's given by this example here, which is Rivera et al.'s Ring of Life. Now, Rivera et al. Were interested in the question, as many biologists, how does eukaryotic life originate, or how did it originate? And they did some study, and they found a number of phylogenetic trees, 5 of them, which are most probable, according to their study, are given here. Now, I'm not a biologist, so please don't ask me what these symbols are. I know that Y1 and Y2 are probably yeasts, and H is Heliobacter, but with the others, I have to follow Barbara's lead and say, well, I have to either write to Rivera et al. Or look it up in the paper. So Rivera et al. Came up with these 5 probable phylogenetic trees from a study of 10 bacterial genomes, and they concluded that in its early life, in its early stages, life was more like a network than a tree. So we then asked the question, well, how much does this result depend on the fact that the trees they were looking were all on the same taxa set? So what we did was we started playing around a bit and removed taxa or leaves from these 5 input trees. And we, for example, looked at the trees you get by removing all those taxa, which are marked by a square. So for example, in this first tree, we removed this one and that one. In this tree, we removed this one and that one, and so on. And it turned out that, in general, if we looked at the partial trees by removing those taxa marked by a square, we actually do get a circular split system, because the 5 trees you were seeing in the previous slide, they're actually circular. And the network we are generating, or the splits we are generating and then displaying with a phylogenetic network drawing program like split tree is the one you see here. And this is actually Rivera et al.'s Ring of Life, except that you have to remove this interior vertex and all incident edges. So if we remove those taxa marked with a square from our trees from before, our my and my inference will to recover Rivera et al.'s Ring of Life. Now we also applied it to our trees, our special trees, to Q-imputation, and we did get not the complete Ring of Life, but just some split, but not all of them. We also applied it to the C supernetwork method, and we were quite surprised that the C closure supernetwork, which usually works quite well, in this example produced this rather complicated network, which was quite surprising to us. Thank you.
We have time maybe for one question, please. No questions?